Hello, we are Team 11 and our project was to design the epoxy potting caps for a capillary filtration system.
Capillary filtration is just one step in an industrial water filtration process. It occurs after large particles are removed from the water but before water is sanitized, and primarily removes undesirable particles such as iron and magnesium. The filter consists of two materials: thin, hollow silica glass fibers encased in an epoxy that holds the fibers together. The feed stream of water passes through one end of the filter, and clean water is filtered out through small pores in the capillary fibers, often in multiple passes through the water filter. Capillary filtration is just one step in an industrial water filtration process. It occurs after large particles are removed from the water but before the water is sanitized, and primarily removes undesirable particles such as iron and magnesium. The filter consists of two materials: thin, hollow silica glass fibers encased in an epoxy that holds the fibers together. The feed stream of water passes through one end of the filter, and clean water is filtered out through small pores in the capillary fibers, often in multiple passes through the water filter.
To manufacture a capillary water filter, liquid epoxy is poured onto the delicate glass fibers and allowed to harden, a chemical process known as curing. Epoxies are a type of polymer created when a resin and a hardener are combined and allowed to cure. They are thermosetting polymers, meaning once they are hardened, they cannot be reheated and reused with the same functionality. Common epoxies include adhesives, paints, coatings, and sealers. The problem with using epoxy potting for the water filter is that the curing reaction is very exothermic, and as a result, heat builds up within the reactor. This heat is transferred to the glass fibers, causing them to break due to an accumulation of thermal stress.
The initial goal of this project was to develop an understanding of the kinetics of the epoxy curing reaction and to model this reaction in COMSOL with respect to the geometry of a capillary water filter. To appropriately evaluate the model, we had to create a temperature profile of the reactor as a function of the curing time. Our end goal was to design a strategy to prevent the glass capillary fibers from breaking under thermal stress while limiting changes made to the functionality of the water filter.
The most accurate model for studying epoxy curing reactions is Kamal's model. This differential equation allowed us to determine the degree of curing, alpha, as a function of time. The reaction constants were calculated using the activation energy and frequency factor of the epoxy. The total heat associated with curing is also a known parameter, allowing us to calculate the heat released at any given time throughout the reaction. Kamal's model was developed through patterns in empirical data gathered by differential scanning calorimetry.
DSC is a technique used to determine physical properties pertaining to the enthalpy of materials, such as heat capacity and flux as modeled below. It also allows for the determination of how the extent of curing changes over time.
Using COMSOL, we were able to build our desired geometry and define the materials associated with each domain. We applied Kamal's model to the epoxy and generated temperature profile graphs to examine the heat flow from the epoxy to the remainder of the reactor. A real capillary water filter would consist of several bundles of these hexagonal shapes, as you can see on the right, but for modeling purposes, we focused on one hexagon.
We varied three parameters to determine the best possible solution for the problem. First, we varied the material used for the capillary fibers. To determine the best possible material for these fibers, we ran the model with materials commonly used in water bottles, such as aluminum and silicone.
The next parameter we altered was the initial temperature of the reactor, which also determines the length of time it takes for the epoxy to cure. We ran the model with initial temperatures ranging from 360 to 400 Kelvin at intervals of 0.05 hours to determine the maximum initial temperature that does not cause the reactor to exceed 425 Kelvin.
The final parameter we studied is the addition of a filler material to the epoxy. We chose polylactic acid, or PLA, as the filler material because it is food safe and has excellent thermal properties for the system's range. This reduces the volume of epoxy required and allows the filler material to absorb additional heat from the curing reaction. We began this study in COMSOL by varying the porosity of the epoxy in 10% increments, down to 50% where structural stability may be compromised.
For our final model, we chose to keep the capillary fiber material as silica glass because it's the safest and most economical material to use. The ideal ratio of filler material is 50% PLA to 50% epoxy. Under these conditions, the ideal initial temperature for the reactor is 382 Kelvin, which leads to a total curing time of approximately 4.2 hours and does not cause the reactor to exceed 425 Kelvin.
Further research for this project would include testing our solution and creating a physical prototype of the improved capillary filtration system. This project is important because developing ways to improve this water filtration strategy can potentially expand access to these filtration systems, ultimately making safe water more accessible.
Finally, we would like to thank our faculty advisor, Dr. Nie, for all his help on completing this project.